and they are the basis for this, we generally don't work with general purpose trees like this. We almost always focus in on binary trees, and more specifically binary search trees, which we'll talk about in a minute. So in this case now, a binary tree, the nodes have at most 2 children. That means that the maximum degree for any node in a binary tree is 2, right? It might have 0 children. A given node might have 0 children, 1 child, or 2 children, but no more than 2 ever. That's why it's called a binary tree, okay? So only 2 children. So down here, you'll notice, well, you tell me, is the thing down here at the lower right of the slide, is this a binary tree, or is there something wrong with it that it is not a binary tree?
It is a binary tree.
It is, right? Looks binary. Why? Because nobody has more than 2 children. This thing has 2 children, great. This one has 1, that's great. This one has 1, or this has 2 children, 3 has 2, 6 has 2, 14 has 1, 10 has that. There's nobody who has more than 2 children, so it is a binary tree, okay? So now digging in deeper, again, a more specific case of a binary tree, right? This is a special case of a binary tree. And that says you have a binary tree and now there's rules, right? A binary search tree is a binary tree that has rules about the ordering. And that ordering says everything that is to my left, that means my left children, right? Everything to my left is going to be less than me, right? Now, duplicates are another matter. We'll talk about the fact that duplicates are problematic. So we're pretending for the moment that dupes don't happen, right? We'll come back to that. So everything to my left is less than me. Everything to my right, that means my right child and below, everything to my right is more than me, right? That's the rule for a binary search tree. So this thing here is not a binary search tree, or is it? Let's look. So 8 is the root. So is this a binary search tree? So is 3 less than 8? Yes. Is 1 less than 3? Yes. Is 6, notice 6, 7, 4, those aren't bigger than 8. So everything on the left, in fact, is 6 bigger than 3? Yes. Is 7 bigger than 7? 6 bigger than, or 7 bigger than 6? Yes. And 6 and 4, yep, that looks right because everything to the left is less. 10 is greater than, 14 is greater than, 13 is less than 14. So this, in fact, is a binary search tree. It's a binary tree, we know, but it is also a binary search tree because it adheres to the rules of ordering that go with a binary search tree. That was a lot. Okay, so any questions about that idea of what constitutes a binary search tree? Everybody's good, or everybody's quiet? Okay. Okay, so the next piece then is, there's one more term, and that is a height balanced tree, okay? A height balanced tree says that the height is, if you look at the left side and the right side, that the height is within 1 distance. If we check the height on the left and the height on the right, the difference between those two can be at most 1. So now let's see, is this not only a BST, but is this a balanced tree? So let's see. So let's look at the height going toward the left, right? So if I just count on the left side, 1, 2, 3, okay? Height on the right side, 1, 2, 3. This is a height balanced tree because if you look at the left side, the height is 3. If you look at the right side, the height is 3. It's within 1. It's still considered balanced if 1 is 2 and 1 is 3, or 1 is 1 and 1 is 2. It can be off by 1, but it can't be more than 1. If it's 2 or more, then obviously it is not height balanced. Okay, we're going to talk about why that's so important to us algorithmically, but we'll get there soon enough. All right, questions there? Okay. All righty. So now let's talk about how you walk through a tree. Okay, but I want to make sure really everybody